Howdy, folks. This is going to be my second kind of YouTube intended video. What I will be covering is star transformations, why they transform, how they transform, and why they do the things they do. I will be having my whiteboard to kind of describe and show like the transformation steps. Um, so this is going to be a tad bit different than my usual TikTok videos. My TikTok videos are usually about theories, quick information, and I know quick doesn't really fit with 10-minute TikTok videos. But just a quick disclaimer, this is probably going to be longer than 10 minutes. But it is really interesting. I will explain everything in depth just so you shouldn't be confused even if you know nothing about space. Um, so let's get started. Alright, like I said, this could be my whiteboard. This one could be describing things on, explaining. But first, we're gonna have a gas cloud, right? So we have this gas cloud here, and this gas cloud is filled with just dust, ice, like just the fundamentals for a solar system or like a star at least, like hydrogen, helium, nitrogen, all that stuff. All right, so when this gas cloud gets affected by a shock wave, aka a supernova, which I will be getting into, when it gets affected by a shock wave, that's a shock wave. Um, it starts to kind of collapse on itself, not implode, but it's a very unstable cloud. Every gas cloud is, so it starts collapsing on itself. And what this will do is it'll cause this gas cloud to start forming, which will start making a disk, right? So it will start making a circle because all this extra stuff, a part of the gas cloud, it's going to start spinning around that one center point. You know, like we look at Earth or something, it's a sphere, right? There's a center core. We spin around that center core, things get dragged into it. It will start making a center core. And with this reaction to it, what will start happening is it will start forming something called a nebula. A nebula is whenever it starts, it's kind of like a sphere. Like if you look at Earth, it's kind of like a sphere, but it's kind of wider around the center, right? And so it will start raising its temperature by hundreds because this is a lot of heat, a lot of friction, no oxygen to disperse the amount of energy or heat that is being put into this. And then it will start forming something called a protostar. A protostar is kind of like a center point with like a disk, right? So not Saturn. Saturn has rings. But it will start spinning very rapidly like this. Not like up and down or like vertically, very fast horizontally. And this is just still filled with a bunch of dust. I mean, like, think of our sun in 98 or like I think 98 or 99% of our solar system. This sun alone is in this chunk or is in this gas cloud. So, we're not talking about some like a gas cloud Earth size. We're talking about this giant, just random gas cloud in space. It will start getting very, very hot. I think up to 150 million degrees. Can't remember if that's Celsius or Fahrenheit. Um, oh, sorry, 15 million degrees. It'll get to 15 million degrees, which still is extremely, extremely hot. This will eventually lead to the spreading of the planets because this disk, this center disk, will start stretching out more and more and more. And then you got your like main sun, then you got like your planet, and then another planet, because these gas channels that are less dense than the center will start orbiting around that middle core. And then whenever those gas clouds or those gas like rings start clumping into the more dense items, it will start creating planets or celestial bodies. And the reason for that is because obviously the denser or more mass something has, the more gravity something has, right? So, after it's done doing all of that, you got your main star. So, we're just going to use ours, right? The sun. So, now you got the sun. And like I said earlier, this is 98 or 99% of our solar system. So, this took up most of that gas cloud. And just a little disclaimer, our sun is actually average size. It's an average size sun. There's way bigger ones. But now that we got our sun or our star, it is start going through a reaction called nuclear fusion. Nuclear fusion is to where you have gravity pushing on the center part, and then there's a reaction inside that burns hydrogen or combined hydrogen and turns it into helium. The helium and the amount of pressure that gets exerted from the center point is pushing against gravity. Yeah, let me make it forth here. Now that it's pushing against gravity, there's not equal force, but it will get an equilibrium. But obviously you can't have infinite of something, right? So as nuclear fusion goes on, which is going to be for billions of years, or sorry, not billions of years, like millions of years at most. No, I would say billions, yeah. Um, the star will eventually start running out of hydrogen and helium, and it will start getting compressed. But whenever it starts getting compressed into a smaller and smaller circle, it's going to use the rest of its energy to start expanding. So it's like whenever you get, like, if somebody gets hyperthermia, you feel that warmth before you die, right? Or you start feeling that really good warmth because that's your body using the rest of its energy. So from this really small point, that's getting a bunch of gravity just exerted on it, because you got to think the mass of our sun is now exerted into a small point. It is going to use that, like I just said, that rest of its energy, that dying point, to expand. Now, what happens when this expands? It'll get massive, way bigger than it is now, right? I mean, whenever our sun will go through this phase, it's like 5 billion years or something, I think. It will start. It will definitely reach Earth, at least reach Mars, I think, and it'll just completely eradicate Jupiter. Like, it'll just completely throw off the whole system. Um, no planet is gonna be like it was, at least. It's not. No planet is gonna look the way, like, even the farthest one, like Neptune, completely warmed up, heated up, right? But with this giant star, I wouldn't call it a star at this point. The real term is red giant. With this red giant, it's losing a lot of heat because now it has more surface area, which means the heat spreads out a lot more and leaves the star through radiation. Now, whenever it gets to this point, the star will, like I just said, lose a lot of its heat and it will slowly die out. Once it got to as big as it can, it will either turn into a dwarf star, which will just, it will lose its complete solar system and lose its orbit and will just float off into space. Or what will happen is it goes through a process called a supernova. Actually, no, I'm going to relapse. Whenever it does just float off to space, it will become a dwarf star and it will just slowly cool down. And eventually just be this black celestial body floating through space that has no heat left. And it just this thing. Um, but if we take a star that's much bigger than our sun, um, it has two paths after uh, the red giant. It has two paths. Both of them involve supernovas. Um, so we got the red giant, right? And say this was the sun's original mass, or this was the star's original mass, the center core circle, that was its original mass, and now it's expanded into this red giant. If it has a way higher density than our sun, it will either turn into a neutron star or a black hole. I think there's a couple transformations in between those, but those are the two main ones I want to talk about. Now, whenever it does go through that process, a neutron star is whenever it collapses into a supernova. So imagine it expands. So basically, what happens whenever it does a supernova is say the star is like this size, right? And then it slowly starts dying off into that size. And then it will expand again really big. And then a supernova will go completely collapse on itself. And the amount of sheer energy and density and mass that just collapsed on itself is fighting to stay balanced. It will cause this massive just shock wave all throughout space. It'll cause this massive just shock wave all throughout space, which will end up actually, if it reaches it, reach another gas cloud to cause another star or cause another nebula and proton star or protostar. And a neutron star is whenever it doesn't have enough density to form into a black hole, but man, still a bunch of density. It is a very hyper fixated ball of just pure energy and light. It, like, if you put a neutron star in our solar system, it would throw off orbits. It would probably be like so much stronger than our sun's gravitational pull. That's why we never see any solar systems by a neutron star. It is just this very strong source of power, and it's just like imagine okay, imagine a twig next to a tree. Say our twig is the sun, or say the twig is our sun. Do you think that twig, if you hit against the tree, do you think the tree is going to split in half or the twig? The tree, the giant redwood tree is a neutron star compared to our little oak stick. That's the only analogy I can really think of to compare a neutron star to another celestial body, another mass celestial body. So if you were to look into space, neutron stars are really cool. I love neutron stars. I'm probably gonna make a video on them, honestly. But to our next point, black holes. Black holes are really interesting too. I mean, whenever you think of a black hole, you seriously think of just this void in space that inhales everything it sees. Slightly exaggerated, and I'll explain why. But it goes through the same process. Supernova goes out, and then it whips back in, makes that giant shockwave all throughout space. But it has enough density to seriously collapse on itself, but not exert all of its energy. It just keeps collapsing on itself, right? And with this constant energy and just massive poolingness, it has the strongest gravity or the strongest gravitational pull out of any other celestial body in the universe, in the observable universe. Sorry. Um, Now we don't know where black holes lead. We don't know what happens when you go into a black hole. We do have a theory called spaghettification. Um, it's whenever if you fall into, say this is a black hole, right? If you fall into a black hole feet first, your body, it's seriously going to change the time, right? So time will be moving faster near your feet than the top of your head. So it'll pull and pull and pull and pull, then split your body in half. And then when you're farther in, it'll split in half again and again and again and again and again. It'll just stretch your limbs. It's very gruesome for a natural cause. But how a black hole kind of functions is since it's repeatedly collapsing on itself over and over and over again. Like I said, it has the strongest gravitational pull, which means it can bend literal light. But that doesn't mean it grows. When everybody thinks if you throw something in a black hole, it'll just grow. Yeah, no. I mean, our galaxy would be completely destroyed. We have a black hole. I can't remember what it's called. Um, but yeah, if it just grew when things entered it, we would be absolutely destroyed. I mean, there would be no galaxies because black holes would just be constantly eating everything. But it is so powerful that it can bend light. Now, light moves 186,000 miles a second. It can loop Earth 7.8 times. Think about that. 7.8 times in 1 second. I can't even I can't even probably walk or get to the end of my board in a second. Oh, second passed. Light just traveled around Earth 7.8 times. Um, but somehow the black hole can catch it and completely warp it around its around the horizon line. The horizon line is like whenever you see a black hole and say this is light entering it, this little line here, or the defining part from the circle, or the oval, I should say, is the horizon line, right? But what happens is so you have light traveling across space, right? Light doesn't have a defined stopping movement, like one Newton's laws. Um, can't remember exactly the word, but it's basically something in motion cannot be stopped unless it's something restricting that motion or resisting that motion. And in blank space, you're not going to see anything that resists light's motion unless it's a planet or something. So if you see light going straight down, right? Imagine light goes straight down, and then you have a black hole. The light will quite literally, slowly and slowly get caught around the horizon line until the more light does this, and then it'll go again, and then again and again, and that's how you get your giant for the giant black holes out there. I think it's called Ton 618. The giant black holes out there, you get these rings of light that goes vertically across the black hole and horizontally across the black hole. Um, Now, say you are a planet that can somehow be close to a black hole but resist its pull. So, say this is the black hole, right? And you're at that perfect distance, like right here, without getting pulled into a black hole. The black hole's gravitational pull is so strong that a couple things happen. One, time will move much, much, much faster on this planet than it does on say this is Earth, this little dot I'm gonna make. Say that's Earth. Earth is so far away from the black hole. And so imagine Earth stays 24 hours, right? Now, if we tried putting that calculation, 24 hours, into this planet, 24 hours would probably consist of like 30 days, even more. Say there's an hour on this planet, each hour on this planet would be a day on Earth. That's how badly it would affect this planet. And that's how badly the gravitational pull would affect that planet. I mean, if you've ever watched Interstellar, very good movie, you can see this on the ocean planet. So, first thing, time. Black hole affects time. Second thing, a black hole also affects the planet's stability. So say we did this millions of light year journey across our galaxy to this theoretical black hole and this theoretical planet, or sorry, not theoretical, imaginative black hole, imaginative planet, right? And we're on a spaceship. If this planet is as close as it's depicting, obviously not directly proportional, but say the distance from Neptune to our sun. So that would be like 10 astronomical units, but that's for another video. Say this spaceship, this black dot right here, goes to land on this planet. It's so unstable because this black hole still has an effect on the planet, right? That with that slight movement on the planet, it will cause the planet to actually shift and go slowly. Sorry, that's gonna go slowly, and I mean slowly. We're not even slowly, sorry. And I mean like it will just get dragged into the black hole. It will start orbiting it and then gone. Nobody knows where it goes though. Is there a white hole that like opens up at another side of the universe? Is there a pocket universe that's filled with white holes instead of black holes? Think about that. There's one of me's talk about what happens when someone goes into a white hole. But it would be very different because white holes would exert stuff, right? So in that universe, it would be normal just to see things popping up in space. What else is there to say? There's obviously much different sizes to black holes. Like I said, the biggest one I think is ton 618. Don't quote me on that though. Like I said, these are just three main star transformations. They're not any. I think there's a couple in between them. These are just the big heavy hitters. I'll probably be making another video on the more specifics into each of these transformations. But yeah, this is my second YouTube intended video. So if you watch it all the way through, thank you. And I hope y'all have a good day or night, and see ya.